specifically look at this, but they're all the same. Notice that if I take this power and multiply it by 2, I get this power, which means this should be denoted by y, because this is y squared. So now this is very easy. Y squared minus 2y plus 1 equals 0. And we know that this is a perfect square, which is y minus 1. So although it's quadratic, although we expect two solutions, both solutions are the same. Y equals 1. And then I go back, x to 3/4 equals 1. And there is only one option, x equals 1. So these equations are not quadratic. We say they are quadratic in form. In other words, I can make it very easy by using the notation for this y, because I realize that this is y squared. So if you square this, it's like you multiply the powers and you get this power. So if this is y squared. And this is easy. And when we factor, we get this. So we have two solutions, but actually only one because they are the same. And then we have x to 3/4 equals 1. And we raise both sides to the 4th power. And then we take the cube root, so there is only one answer. Good pick. Okay. Again, if we want rationals, they're on page 122. So because we did not specifically work on this situation, just a little bit, I did not put a problem like this one on the final exam. They're not difficult, but we just I did not see a lot in the homework, so I did not spend too much time on it. Good. Anything else? You want to look at rationals again or something else?
Can we go over the linear inequalities?
Linear inequalities, sure. Linear inequalities. They are on page 205. Good.
Can we do 45?
Yes. Let's work on 45, you said. Very good. In 45, we have x minus 4 over 6 greater than or equal to x minus 2 over 9 plus 5 over 18. So remember how we addressed this? I see fractions, I don't want fractions. But I realized that 6, 9, and 18 have a very nice least common denominator. Oops. And that is 18. And I will multiply each and every fraction by 18 over 1. 18 over 1, 18 over 1, and 18 over 1. When I simplify, I get a 3 to be multiplied or distributed here. When I simplify, I get a 2 to be multiplied or distributed here. And when I simplify, there is nothing. It's just 1. So this is always the idea. When I see an inequality or an equation with fractions, I should always try to get rid of them to make the equation as easy as possible. So now when I distribute, I have 3x minus 12 greater than or equal to 2x minus 4 and plus 5, which is way more doable than this. Easier to handle. Yes, I will combine like terms first and plus 2x plus 1. Yes, I have to move the term with x to where it belongs and the other term to the other side. So then I have x here greater than or equal to 13. And that is fine. And I will write x in bracket 13 to infinity. So even if this looks complicated, difficult, cumbersome, it's not. Once I eliminate the fractions by multiplying each and every one of them, fractions or not, each and every piece has to be multiplied by 18, it became just a simple situation. Good pick. Good. Next question. Next topic.
Can we do an exponential growth and decay word problem?
Yes, very good. They are at the end of 4, chapter 4. And the page is, I don't think we have anything left, but we'll find something. 532. Good. So half-life and the decay are here. We looked at aspirin, I think. We looked at lead. We can look at Xanax. A bird species in danger of extinction, which is also decay. And the exponential growth. It's all about half-life here. Okay. I think we looked at Gaza and Israel. It's up to you. Plutonium.
You can do a decay example.
Sure. Anything. Half-life of krypton, 91. Plutonium, they're all decaying. Look at this. The half-life of plutonium is 25,000 years. So
I was gonna choose number 18.
That's fine. That's fine. So 16 grams will become 8 in 25,000 years. Unfathomable. So we're on page 7. Good. So the half-life, so this is 18. Age or the half-life, this is not hours. Age is the half-life, 25,000 years. Okay, fine. So we have a mass, M0, of 16 grams. Fine. How many grams are present after 25,000? After 50,000, after 75,000, after la la la. So we will have 8 grams after 25,000. Another 25,000 will have 4. So that will be 50,000 years. We're going to have 2 grams in another 25,000 years. We're going to have 1 gram in 100,000 years. So this is not really a problem. It's just trying to make sure that we understand how this works. So it gets halved every 25,000 years. And 50,000 is going to be here, and another 25,000 is going to be here, and so on and so forth. So the actual decay model will be something like Xanax, for example, which we didn't look at. And the exponential growth will be like the population of New Zealand. Because we looked at aspirin, we looked at lead. I don't think we looked at thorium. 7,340 years is the decay, the half-life. So what do we have in mind? Anyone would like to choose? Which one?
28.
28, very good, the thorium. Okay, very good. So 28 on 532, good. The half-life of thorium is 7,340 years. Okay, how long will it take for a sample of this substance to decay to 20% of its original amount? So the original. And you know that the model is the same. A of t equals A0 e to kt. It's just that this has to be negative for decay. Negative for decay. And positive for exponential growth. Why can't I find the correct direction? Okay. So remember, the half-life is natural log of 1, I meant k, is natural log of 1/2 divided by the half-life. So k, the decay rate, has this formula. I don't like the formula, I like to start from scratch, but you can use the formula if you like. Just make sure that since it's decay, it's a negative number. If it's not a negative number, something is wrong. So I have this and natural log of 0.5, same thing. Natural log of 0.5 divided by the half-life. Once I divide natural log of 0.5 by 7,340, I get the decay rate. So natural log 0.5 divided by 7,340. Okay. So be very careful now. Read the entire number. This is power 10 to negative 5. So k equals negative 1, 2, 3, 4, 1, 2, 3, 4, 5, 4, 4. Because it's 10 to negative 5. So I have to move the decimal digit. 1, 2, 3, 4, 5. So it's very small. Very, very small. So now I have the model. A of t equals A0 times e to negative 0.40944 t. Now, I'm asked, find the time. So to get to from 100% to 50%, this is the amount. To get from 100% to 20%, it must be way more number of years. So from 100 to 50%, 7,000. But from 100 to 20%, it has to be more than 7,000. So I will replace A of t by 20% of, which is multiplication, 20% of the original amount. and create an equation and find t. So that's 8. So 0.2 a0 equals a0 e to negative 0.1234944 t. Of course, the original amount does not matter. And now I can apply natural log to both sides. And I should definitely get way more than 7,000 years. Okay, so natural log 0.2, when I apply it here and I bring it down, natural log e disappears because it's 1. Not 0, it's 1. So I have natural log, and make sure that the time you are not getting a negative number. That would be terrible. And you have to put the parentheses in the calculator. Although I proved myself wrong last time, the calculator works even without. It should not, but it does. Okay, so we have natural log 0.2 divided by negative point. Oh, you know what? I'm going to ask the calculator to use the whole thing for the best approximation possible. So I'm asking the calculator to enter the whole thing. So when I press enter, I get 17,043 years, almost. As expected, because it drops from 100% to 20%. From 100 to 50%, it needs 7,000. Good. So this was the exponential decay. Are we looking at anything else here? I don't think we did the growth model with the New Zealand's population. If you want, we can, or something else.
Yes, can we do number 35, please?
Yes, of course. So it's the same model. In 35, as we know, A of t equals 4.8, which is the original, times e to 0.0082t. And of course, because it's an exponential growth, although it's tiny, it's exponential growth, the rate is positive. If it were negative, the population would have gone down. Okay, so then it says, what is New Zealand's growth rate? Oh, it's okay, and it says millions t years after 2020. So I make myself a note, t equals 0 represents 2020. And this is the k, or the growth rate, 0.0082, or move 2 decimal digits, 0.82%. Okay, now it's asking how long will it take New Zealand to double its initial population. This is the initial population, 4.8 million. That's A0, or A sub 0 if you want, in millions. So 4.8 times 2, and I don't have to multiply it. I know what it is, but 4.8 times 2 equals 4.8 e to 0.0082t. It will be a waste of time to even multiply. It's the same procedure. So all I have to do is apply natural log to both sides, bring down 0.0082t, and divide. Natural log 2 over 0.0082. I do not need parentheses around this because it's positive. But the calculator should not accept without parentheses if it's negative, but it does for some reason. Okay, 0.082, and this is it. So in 84 years, 84 and a half years roughly, so in 2020 there were 4.8 million. Did I forget to share? Oh no, sorry, I'm sorry. So it's natural log 2 divided by 0.0082. So in 2020 they had 4.8 million. If they want 4.8 times 2, which is 9.6 million, they will have to wait for roughly 85 years. So in 2020, 100. I'm sorry, in 2100,